Okay, let's go and get started. I'm going to give you guys a lab today and give you some time to start working on that. But first, I do want to cover just a little bit of stuff today, go over a few definitions, and then we're going to dig into working on that lab. So let's go and get started. All right, so the first thing is we had this abstract communication system diagram before, and you can see there we have a source, a transmitter. The source is kind of the source of the information we're transmitting. The transmitter is what takes that information and encodes it in some way to put it on the channel. The channel may be subjected to some sort of noise. It could be electrical noise on the wires, like capacitance or RF interference or something like that. It could be any source of something that changes or damages the signal in some way. Then we have the receiver that takes the information off the channel and decodes it, and then the destination is where we now have the information going through. So we've also defined a few other things. We defined these previously, time division multiplexing, or TDM, which is essentially what Baudot's 5-unit code was doing. You have 5 bits, but one wire. How do you get 5 bits to fit on one wire? You put them on 1 bit at a time. Divide up the time. So this slice of time is bit 0, bit 1, bit 2, bit 3, bit 4, and then all together we've had our 5 bits. The baud rate, also known as the signaling rate, is how often there is a change to the channel. If it's a wire, it's how often do we, at maximum, how often do we change the state of it. The data rate is how much data we can fit through that channel. In other words, how much, going back here, how much source data goes through the channel per second, rather than how quickly are we changing the channel per second. Notice those are different. They may be different because the source, for example, could be, I don't know, like Baudot's 5-unit code, but then with a transmitter, it goes through that. We have to add a start bit, add a stop bit period. So now we have 7 time periods for only worth of change for only 5 bits worth of data. So they might not match. Sometimes the data rate might be lower than the baud rate. Sometimes the data rate could be higher than the baud rate, depending on our signaling paradigm. The framing bits, those are the start bit and the stop bit, also any parity bits or anything like that. The framing bits are just the bits that surround the data bits. The data bits are the actual message that's being encoded. And a serial data unit, or SDU, is that entire thing. It includes the framing bits wrapped around the data bits. And then asynchronous serial communication is the method of communication where you have a start bit to resync the message, a stop bit to return it back to the idle state, and you're sending that using TDM. So these things all relate to each other in some way. Okay, some new concepts and new definitions here. So asynchronous literally means without respect to time, but in practice what it really means is without a shared clock. In other words, we use the start bit to resynchronize. So you still have to have an agreed upon timing if you're using asynchronous serial communication, because all that the start bit does is resync the clock, but then you have to time the same amount of a bit period on the sender as you do on the receiver to get the data to go through. All right, synchronous communication, on the other hand, is a communication system that uses some sort of shared clock. And that shared clock signal could be another wire that's going up and down to be the clock. It could be something else entirely. But there are various paradigms for that. We're going to look at some synchronous communication in a little more depth next class. And then there's also a kind of asynchronous called true asynchronous, which not only doesn't have a clock, but it has no shared clock, no independent clock, no resynchronization needed. And that requires us to encode the data in a way that just doesn't need some sort of clock at all. And there are a few ways of doing that with extra lines for handshaking bits and things like that. So it doesn't matter at all what rate the things go at. But we'll talk more about that later on in the semester as well. Okay. A couple other new concepts and definitions that I want to get in before we take a look at the lab is simplex communication. Simplex means one way. So one way, it means you have a transmitter, you have a receiver. It can only send data from the transmitter to the receiver. And then there's a thing called half duplex, which what half duplex is two-way communication, but only one way at a time. So A can talk to B, B can talk back to A, but they can't talk A to B at the same time B is talking to A. And an example of that would be something like a walkie-talkie. You click on the key, you talk, you can't hear what they're saying while you're talking, you let off it, and then they can use that channel and click their key and talk, and then you listen while they're talking, which is why walkie-talkie communication has like those things like kind of handshaking messages like 10-4 or whatever to say when you've got the message, and call signs and things like that. But the idea is that half duplex might exist in a wired communication or something as well. We have a set of wires. This one talks that way. This one talks back the other way. And actually, something like USB works like that, that the data can come from the PC to the host then, or from the host to the device can then talk back on those same lines. But you can't have them talking in both directions at the same time in a USB 2.0 anyway. And then full duplex is two-way communications where both ways can happen simultaneously. So something like that would be a telephone. You can be talking while they're talking. You can talk over each other. You might not be able to get the message through if you're all talking over each other. But that's the idea, is two-way communication both ways simultaneously. Okay. A couple other things that I want to get in today is this concept of what's called topology. And topology is not really something like we had over here, where it's the kind of the organization of the communication. Topology describes kind of the structure. And that structure could be either physical with how the wires are connected, or it could be logical, meaning how they're thought of in a software or in a network or in addressing. So for example, point-to-point is probably the simplest one. That's kind of the same that we had over here. These are all various forms of point-to-point communication. Point-to-point means you have two nodes and you have some channel that connects between them, and you can communicate between the two. Could be simplex, could be half duplex, could be full duplex. But then we also have a bus where you have, rather than the channel only shared by two things, channel shared by a whole bunch of different things that can all access it. So this one can talk while these ones all listen, and this one could talk while the rest of them listen, and so forth. And so bus topologies kind of have a single shared channel shared amongst, rather than just two nodes, n nodes. Moving on from that, we have a star, where there's a central kind of hub node, like a network hub or a network switch. And then all of these things kind of connect into that central one. So if this one wants to talk, it has to go through the hub. And the hub either relays a message out to everybody, or it switches the message, acts as a router to route the message to a specific location. And then there's a mesh topology, which can have some group of nodes, some group of connections between those nodes. And a partially connected mesh has some of them not connected to every other one. And this is kind of how the internet is organized, is this large, partially connected mesh. Now, a couple variants of that that we see over here. Well, the next one is a ring topology, where they're connected kind of in a circle, which is kind of like a bus that connects back to itself, you could think of it. But rather than a bus where it's all a shared channel, they each have kind of a shared channel to the next person in the ring and the previous person in the ring. And there are physical and more logical systems that work like that. Like there's a type of communication called token ring, where this one can talk and pass a message forward in the ring or backward in the ring. But it's his turn to talk when he has the token. And when that one's done talking, passes the token on to the next node in the chain. And that one talks or doesn't, passes the message on the token onto the next one. So only one at a time is ever getting a chance. And these are used a lot in kind of high reliability environments, because it guarantees that each one of those nodes is going to get a chance to say something. Whereas if it's a bus and this one takes over the bus and kind of just dominates it, doesn't let anyone else talk, then there could be some important message here that doesn't get through in time because somebody else is using the bus. But here, this one gets a certain time slice on a token ring and passes the ability to talk to the next one. All right, there's also a distributed form of the bus, which is still a bus, but notice it's got like buses branching off of a bus. A lot of industrial networks work with something like that, like an RS-485 system. Industrial networks a lot of times will have a distributed bus topology like this. There's also a distributed star topology, which is kind of like a star that has other connected stars to it. And then there's a mesh topology that's fully connected, where all of them are connected to every other one. There are also a lot of hybrid technologies where you might have, I don't know, like a star that has buses coming off of it, or a star that's connects to, with a single thing, to some sort of partially connected mesh. And the internet itself is really this large collection of different topologies all wired together. Some of them might be bus, some of them might be star. There might even be rings connected onto that, or distributed model like these over here, or other variants of that. There may be tree hierarchical architectures like trees as part of this. But the idea is a topology is kind of like an organizational structure, either physically with how the wires are connected, or logically, meaning how they talk to each other and how they address each other. So for example, you could have a bus topology, but it's implemented using wireless, meaning that each one that talks, all of them can hear that one talking and receive that message. They all have to use that same channel. But you could also have a partially connected mesh topology, where this one can talk to that one, but these other ones can't be talked to by that one. It has to go through there to get, or here to get over to here. So there's a lot of different variants of this, but it's useful to have some terminology to be able to understand that. And it's also useful to know topology isn't just what the wires look like, it's how it behaves, or how it's addressed, or how it functions, which is what logical topology means. Okay, now a couple final things here, and then we're going to take a quick look at what you're going to do for the lab. And this one is, networks can be either switch networks or broadcast networks. And in the switch network type, they're what are called circuit switched, message switched, and packet switched. And what the difference between those is, it works like this. Circuit switched means that you have, this is how the old phone system used to work. When you would make a phone call, you would pick up your phone and you would talk to the operator and say, hey, I want to talk to so-and-so in, I don't know, Chicago. And they would take your cord, your physical cord that goes to your phone. They'd plug a patch cable into your socket, and they would connect it to the thing in Chicago. And then they would tell the person in Chicago, hey, they're trying to get to this person. And then they would take a physical cord and they would switch it from that office in Chicago to that person you want to talk to, or maybe that field office, and that field office will then connect to the neighborhood, which would then connect to the person you want to talk to. So you would have an actual wire that goes from your phone to your local operator's office through a patch cable to the one in Chicago, out of a patch cable there to eventually to somebody else's house. So there'd be a physical wire connection from your phone that you have here through all the way to the other end. That's the idea of circuit switched, is you're making a circuit. You're switching things to make a circuit from end to end that stays active. What message switched means is you do that, you make that circuit from end to end, but you do it only for the duration of some shorter message that needs to be sent. So you make this, you have this message you want to send, you make the connection, you make the message, and then it disconnects, which I guess is a lot like the circuit switched, but it's kind of shorter in duration than a whole phone call. You switch, you send a little bit of data, you disconnect the switch. And packet switched is kind of a more extreme variant of that, where you're sending a smaller block of data, and rather than it being message switched from end to end, packet switched is interesting because it's only switched from one node to the next node with a packet. So you say, here's this, and this is more like sending a letter through the mail. You make this little packet of information. It goes from one machine to the next machine, and then it looks at the routing information on that, and it sends that to the next thing, sends that to the next thing, sends that to the next thing. So the message is moving one node at a time in this one block in the form of a letter, like a packet. And we're going to dig into those a lot more later. Now, there are also broadcast networks where The message goes out, it gets broadcast, and the nodes receive all of that data, the packet, and they can all either discard it if it's not for them or use it if it is for them. And some nodes may act as a filter or a router, throw out packets, send them on to somebody else, rebroadcast them, maybe like a repeater. Some packets might be multicast and say, instead of saying, hey, this is for this one node here, they might say, hey, everybody, here's this message that everybody needs to be aware of. And the way that the internet works, we'll talk more about TCP/IP in a few weeks when we actually go to write some programs to program TCP/IP. But really, you can actually send broadcast messages in a lot of cases as well, and we'll talk about that. But you cannot send a packet that goes to everybody on the internet for obvious reasons. But we'll come back to these later on, but I just want to get some terminology in today. All right, so now we're up to the second part of what we're going to do today. We only did 15 minutes on the kind of lecture stuff that we just did. But what we're going to do for this lab is we're going to establish a channel from one board to another board. And we're going to be using the Arduino boards to do that, and we're going to be writing a little bit of code. So we're going to connect two Arduinos together with a wire, and that wire is going to act like the channel. We're also going to need to connect the grounds between the boards, and that's for, well, physics reasons, that if we have want electrons to go from one place to another, there has to be a return path. So we need to have a shared ground between them. So we're going to have two wires, one that's the channel and one that's the ground that allows it to conduct and make a conduction loop between them. And you can kind of see that. That's how a light switch works. When you flip the light switch, it makes a contact that allows electrons to flow through a loop. When you disconnect it, the electrons stop flowing. Same thing, you press a key on your keyboard. You push the key down, makes a connection, electrons flow through, disconnect, but you need two wires to have that flow happen like that. You need to have a return path or ground. Now, in the old days with telegraphs, you could make an earth ground by pounding a giant conductive pole into the actual earth, and it acts as kind of a sink for those spare electrons, just like lightning striking, going into the ground. You could do that, but in our case, we're just going to run an extra wire from ground to ground of the two boards. And really, if they're connected through your laptop, the laptop could act as the ground with the USB cable acting as the ground between them, but go and connect the grounds anyway. All right, let's take a look at the lab sheet, and then we'll do some Arduino Basics. So I'm going to take a quick look at the lab sheet. Give me a second here while I bring that up. Okay, so here's the lab. Oh, hold on, I'm in the wrong place. Give me a second. Oh, and I gotta switch this over. You can see what I'm talking about. All right, here we go. All right, so here's what the lab looks like. Hold on, that is not the lab. I'm going to pause this and bring up the. Okay, here's the right lab. You should have already done lab 1. You should have your materials and your supplies. You should be ready to go. And this, it says you can work in groups of 2 to 6 people here. I'd really rather you work alone or with one person on this lab. But if you, and that's for safety reasons as well as reasons why I want everybody to understand this and have gone through this, because the later labs you're going to have to do individually. This one, I gave a little more flexibility just in case you don't have all your equipment in, you don't have all your things in, and I want to get this done by next week, within 1 week. So I'm allowing a few more people to work together on this one if you need to, but try to do it yourself, try to submit it yourself if you have the equipment to do it. It'll help you in the long run to have done this and know how to do that. All right, so first off, you're going to be setting up the development environment for the Arduino Uno by installing the Arduino development environment. So to set that up, follow the instructions that are here. Really, you can just go type Arduino application installation or whatever and install. Google will find it for you, and you can do that. But you can also follow this how-to guide on this Instructable site to do that. So once that's complete, you're going to write two separate programs. You're going to write a sending program, and you're going to write a receiving program. So the transmitter in this case is only going to configure a general purpose I/O pin. So it's going to configure one pin on the Arduino to act as the I/O. And you're also going to configure the LED pin so you can see the light change high and low. And in fact, on the Arduino Uno, the LED and the GPIO are actually connected to the same pin. So if you wanted to, you could just wire those, use that pin and wire it together. And we'll talk more about how you do that here in a second. The other part of this is in the loop part of the transmitter. You're going to read a key from the serial interface of the PC. If that key is a 1, then you're going to set the general purpose I/O pin high. So when we hit 1, enter, in the serial control panel thing, then it's going to set that pin high. In other words, a physical pin is going to change its voltage in the real world. When you press 1 and hit enter, when you press 0 and hit enter, it's going to turn back off. So we're going to turn it on, we're going to turn it off. And on any other input, we're just going to ignore it. On the receiving end, it's going to be set up the same way, except the GPIO pin is going to act as an input, and it's going to read data off of it. And we're going to read the logic level of that pin. If the input pin reads high, then we're going to print high on the terminal. If the input pin is low, we're going to print low on the terminal. So in other words, we're establishing a channel. So one board can change the level up and down. The other board can sense the level and say, oh, high. It's high, it's high, it's high. If it goes low, oh, it's low, it's low, it's low, and so forth. And it says demonstrate the working system. You don't really have to demonstrate it to me, but submit the code in a zip file for both the transmitter and the receiver. They call them sketches. They're really just the source code, but they're in a .ino file, I think it is, which is Arduino. But the idea is you're just going to submit those two programs to me. I'll grade them and get them back. But I want you to make sure you hook this up. Make sure you have that channel established where the one can change the voltage level, the other one can sense the voltage level and display what it is, because we're going to be building on this in a future lab. So make sure you have this working. All right, let's go back and fill in some of the details you're going to need to do this. First off, well, let's just go back to the presentation and we'll cover it there. Okay, so in the presentation, we're back there. Arduino Basics. I want to go over a few basics here, a few programming things. So Arduino Uno is a single board computer that has input and output pins that are available for you to use. They do come in a lot of different form factors of different ones. The one we're buying is the Arduino Uno, and I picked that because it's fairly common. It's a standard size that comes with a USB cord. It's easy to plug in and use. But there are other Arduinos as well. For example, here on my desk for a work project I have, this is an Arduino Mini called the Mini Industrial. As you can see, it's much smaller than the board you have, but it has the same kind of chip on it. It has fewer pins, but the pins come out the back of it. You can see I have wires connected to this, connecting it to one of our sensor boards here. But these are really useful for experimenting with things, trying things, writing microcontroller code. So it's also, if you use that Arduino environment, it's easy to program those. And it's also all built on open source software, free software, and the Arduino hardware is all an open source hardware design or an open spec hardware design. So other companies can make Arduino compatible devices. There are other microcontrollers that are more powerful that support that. It's a very widely used development environment because it's free and relatively easy to install and get working and use and experiment with things. Now, the environment itself, the language that underpins it is based on C and C++, but it has some stuff that it does for us to make things easier. Here, hold on 1 second. I'll be right back with you. Okay. So essentially, like I was saying, the Arduino is based on C and C++ as the underlying language. So the stuff that you learned in 2110, the systems programming class, or the stuff you learned in data structures. A lot of that can be useful for what we're doing in here. The one thing that the Arduino environment does do is it hides some of the details of things, so you don't have to worry about the low-level microcontroller stuff. So for example, it's got some built-in functions that deal with setting the direction of pins. In most microcontrollers, it's done differently, and there's a register that you got to set. It's a data direction register or something like that, or a pin configuration register. That's abstracted away and done for us. So some of those common tasks that you would do in pretty much every microcontroller, every processor, have been abstracted for us, and we don't have to like use a special library or link it in a special way. We can just access those. So let's take a look at some of those features. So looking at those features, the first thing that Arduino programs when you create a new program is it defaults and creates two functions that are created automatically by default. It has a function called setup, and then it has a function called loop. And the setup code runs once when you first reset the microcontroller. When it first powers up, it runs this code once. And then the loop gets called over and over and over again by the code that's auto-generated. So we can write code in here. We don't have to put a while loop inside of here. We just write some code, and we can know that it's going to run it, and then it's going to call that function again. And it's going to call that function again, and it's going to call that function again, as long as the microcontroller is powered on. So we power it up, it runs this once, and then it starts repeatedly calling this function. You think of it like a repeated action goes in here. And so generally setup kinds of things go in the setup. Makes sense, so it's called setup. And things you want to repeatedly do go into loop. Okay, take a quick look at your Arduino board, and it's going to look like this. This is actually the identical one that I suggested you get, but any of the Arduino Unos, the chips on here might look a little different. Some of them might be green, some of them might be blue, some of them might be this dark purple or black color like this one is. But as long as they're an Arduino Uno R3 variant, or really any Uno, it doesn't have to be the R3, they'll look kind of like this. So along the sides we have these little sockets that pins can plug into. And those connect to these pins on the actual processor. So this is a microcontroller. It has a microprocessor. It's got I/O. It's got timers. It's got counters. It's got an A to D converter. It's got a whole bunch of peripherals inside of here. It's got memory inside of there. It's got both flash and RAM. It's got EEPROM. All of that is inside of this single computer system on a chip. This chip up here is just the chip that translates the USB communication into the serial communication to talk to the chip. And then we're going to tell it what we want to do with these pins that are over here. And you'll notice the pins are labeled on the board. And they're also labeled, if you look at the side of these black connectors, they're labeled with a little silk screen on the side as well. So it's very easy to tell what pin does what thing. Now, this is a power connector that you could use with an AC adapter. We're not going to use that. It's going to get its power all from the USB port over here. But if you wanted to have something that like this, that you built some system that used it and you want it to, I don't know, act as a garage door opener or a security system or some cool thing to do whatever you want to do with an Arduino, you could actually power it over this. And when you turn it on, there's no operating system. It just runs the program you put on it instantly when you power it on. It'll start running your code instantly. All right, so the USB port is going to provide power. It's going to give us a way to program it. It's going to give us a way to also talk to it from the PC. And you'll also notice there's a reset button. So if you want to restart your program without doing it through the Arduino environment, you can just hit that reset button right there. Hit that button. When you let go of it, this will reboot this processor. And again, there is no operating system. There's no hard drive. The code is all stored on the microcontroller itself. As soon as you hit that reset button, it'll reset it and rerun the code back from the beginning again. Okay, note again that the pins are labeled on both the board and on the connectors. So these ones here labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Those are digital I/O pins, and I/O means input and output. So those can both be configured as an output, meaning you can change the value high or low, or they can be an input. Read the value if it's high or low. Also notice that this A0, A1, all the way up to A5 that you see down here. Those are analog inputs. And analog, instead of reading just high or low, it can read how high is it or how low is it. In other words, it's a range between 0 and, on this board, 5 volts. So it'll range between 0 and 5 volts. But the question is, how close is it to 0 or how close is it to 5? That's what this analog input can be used for. There are several other pins as well, and the other one we care about is ground. And notice there's a ground pin right here, labeled G and D. There's also a ground pin, a couple ground pins over here labeled G and D. So those are all connected. They don't really, doesn't matter. There's no difference between those. There's also a 5 volt port here. There's a 3.3 volt. There's a reset port, which does the same thing as the reset button. If you pull that low, pull that to ground, it'll reset. And then there's some other things, an analog reference, and so forth. There's some other pins on there we're not going to really worry about. There's also a VIN pin if you want to power this through that pin rather than here or the USB. You could power it from another board if you wanted to. All right, but what we care about is just one of these digital I/O pins, and what we also care about is having the ground connected. So you're going to connect ground to ground. And one other thing that was mentioned in the lab sheet was the LED. The LED is right there. These ones will turn on and off when you're programming it or when it's communicating. You'll see those flicker as it's communicating with the host PC. But there's also this one. That one's connected to general purpose I/O pin 13 right here, the one that's right next to where that LED is. And that LED will turn on or off based on whether the state of pin 13 is high, it'll turn this on, or low, it'll turn that off. Okay, a little bit of the code. Again, this library, this is part of the Arduino library stuff that's built in. You don't have to include anything. You don't have to do anything. Like I said, the Arduino environment kind of abstracts away or hides some of that detail, so we don't have to worry about it. But the first one is this pin mode. So, for example, I could say pin mode 13 output. That sets pin 13, which is a digital I/O, as an output. They default to input. So this sets pin 13 as an output. And then I can do a digital write pin 13 high. That makes it an output, sets it high. Here's a delay for 500 milliseconds, half a second. And then I set it low. So this would make, if I were to put this in the loop code, then what we would see is the pin, well, let's go back. We'd see that light, this is the LED pin. We'd see the LED turn on, and then half a second later turn off, and then half a second later this would continue on. If that was in loop, it would turn on half a second, off for half a second, on for half a second, off for half a second, and so forth. So note that pin 13 is attached to that LED on the Uno board. So the code above would set the pin as an output, turn on the LED for half a second, then turn it off for half a second. All right, Arduino digital input. Pin mode, again, you give it the pin. You say whether you want it to be input or output. That should be all capital, the word processor. Just like output over here is all cap. Here, let me fix that. The word processor likes to autocorrect things. So pin mode 13 input, that makes it so you can read it. And then to read it, you use this digital read function. Digital read pin 13. And that's going to return to us either a 0 if it's low or a 1 if it's high. So when reading the state of that digital I/O, you'll either get a 0, which is, there's a thing already defined that's LOW if you'd rather write low. So you could say if digital read 13 equal LOW, all caps, then we could do something here. So when it goes low, we could do something. We could also do something if it goes high. We could say if digital read 13 equal 1 or equal high, all caps high, then do something about it. You're going to be writing some code like this in your lab on the receiving end where it needs to read the state of a pin and say whether it's low or whether it's high. All right, some other Arduino functions. We already saw delay a couple things ago here with this delay of 500 milliseconds. But there's a delay that when you call delay, it delays in milliseconds. That will delay for an integer number of milliseconds. So if you put 10 there, you'll get 10 milliseconds. You put 500, you'll get 500 milliseconds. You put 1,000, you'll get 1,000 milliseconds, or 1 whole second. There's also a delay microseconds function, which looks the same as delay, but you say delay microseconds in camel case here, and you put the microseconds in here. So that is a higher resolution delay than milliseconds, obviously, because microseconds are much smaller. And this can range anywhere from 3 to 16,383 microseconds. And why is this 3? Well, the reason that's 3 instead of 2 or 1 or 0 is because there's some overhead in calling the function itself that takes up some time. So the lowest you could get is 3 microseconds out of calling this function. So if you call it with 2 or 1 or 0, you're still going to get 3. But above that, you should be able to get microsecond resolution out of it. There's also a way to get the number, get the amount of time since startup. There's a function called millis, which returns the number of milliseconds since the board was last reset or powered up. And there's one called micros, which returns the number of microseconds since startup. And again, startup here is either you press the reset button, or you power it on, or you write a program and upload it to it, and it restarts that program. So it's anyway, it's like the start of when the program that's on there started is what startup is. All right, now how do we talk to this thing through the PC? Well, this is not the channel we're using. This is a separate communication channel from the PC through USB to talk to it. And so to talk to that, we're going to use this serial object. This is a class. It's actually an instance that already is created for us. So we can just, or you can think of it as a class with static methods if you want to think of it that way. But you can just say serial.begin is how, and we give it the baud rate we want to communicate with the serial port on the PC app. And you can pick 9600 or any of the standard baud rates. Just do 9600 for now. Just use it like this. This is going to be maybe too slow for some of the stuff we want to do later. But this is not the communication from board to board. This is just the communication from the PC to the microcontroller through that little USB port thing. And then if you'd say serial.print hello, that'll print that out on the console when you run it. So when you run this program on your PC in the Arduino serial console, you'll see the word hello pop up. Serial.println, print and print line are the same. Print ln automatically adds a new line character for us. We don't have to put \n on the end of this. If we do print, it'll not print the new line, and the next thing we print will be right after that. So it lets you put multiple things on one line. This puts things on a line by themselves. Now, because this is C++ based, this serial.print and serial.println are overloaded, an overloaded method. So you can print a string like we're doing here, just a character pointer, string like we're doing here. You could also print using these a number, a character. In other words, there's a version of this function that can print other things as well. Serial.available, that will return the number of bytes that have come in from the PC talking to it. So these two are from the microcontroller back to the PC. These give us the ability to read how many bytes came from the PC, and then we can read one of them. Reads the first available byte, and we can do something with that. So remember, this is just for communicating with the PC, not another board on the that we're going to talk over the channel on. All right, so here's an example. So this example code, basically notice in the setup, I do the serial.begin of 9600, and I set the pin mode of 13 as an output. And then the next thing I do in loop is I set pin 13 low, and I print out tick. I wait 500 milliseconds, half a second. I set the pin high, and I put talk. So the LED on pin 13 is going to go off. It's going to print tick, on, talk, off, tick, on, talk. It's hard to say. Tick, tock, tick, tock, tick, tock, tick, tock. And that's going to happen as forever, essentially, because this loop code will run forever until we reset the board or take power away from it. And the cool thing about these Arduinos is because it does store the program on that chip, inside the chip, is once we've programmed it, if I just power this up somewhere else without even a PC being anywhere near it, it'll still, the LED will still turn on, off. And if we plug a serial port in over USB, it'll say tick tock, tick tock, tick tock. Oh, let's look at one more other example here. Here's another example that's using a global variable and printing out the bytes that we type in from the PC. So on this end, notice I have, again, serial.begin 9600. I have if serial.available. So if there's a byte available, I read that byte into this incoming byte variable, which I made a global up here. And then I'm just printing it out. I'm saying, hey, print out the incoming byte. And this comma dec, that's printing it in decimal. That's another one of the overloaded functions. You could print it in hex by putting hex there, or binary by putting bin. So these print and print line are fairly highly overloaded functions that can print in a variety of formats and in a variety of different ways. So I'd suggest looking at the documentation for that. Okay, so setting up for the lab, install the Arduino environment on both machines, plug in an Arduino board. Under Tools, Port, select the COM port that's associated with that board. In other words, when you plug that board in, it's going to show up as a COM port on your machine. Under Tools, Board, select the type of board, which in this case is an Arduino Uno. So select the option that says Arduino Genuino Uno. That's the kind of board you have. And now we're ready to write some code for that board. So what I would suggest doing before you start into the lab, write this code, write the TikTok lab program, or not lab program, but the TikTok example program. Make sure that works. Make sure the light turns on and off. Make sure it says TikTok. One quick thing, how do you read that serial data that's coming in TikTok? There's a serial terminal program that's built into the Arduino. You don't need like RealTerm or some other program to connect to that COM port and read that data in and see it. And here, let me quickly bring up the Arduino environment. And I'll show you where that is. Oh, let me switch this over so you can see what I'm doing here. All right, so here's what the Arduino environment looks like. And let me move that down so you can see all of it. All right, so you'll notice here's where you'll write your code. This is a little console window down here where you can see what happens when you program the chip. So this is kind of like the programming compiler window. Any errors you have in your code or warnings, they'll show up down here, like a typical compiler. But to get to the serial monitor program, you click that, which if I had an Arduino plugged in, that would work. Here, let me plug this one in real quick. All right, so Tools, Board. That's, I'm using the Arduino Nano here. Port, I believe this is on COM14. I can bring that up, and this is what this little serial monitor program looks like once you have your program on there. So to send messages, you could type in to here, and then click Enter, and it'll send. And any messages that come in will show up in here. Let's quickly write that TikTok program for this, this particular thing. So here, serial dot begin, and we're going to set it to 9600. And let's set up that one pin for an output. So again, here, let's pull this over so you can see. We're going to do a pin mode 13 output. And this board's a little different than yours. I don't even know if this has an LED, but we'll find out here. Let's see. All right, so serial, or not serial, pin mode, pin 13, output. And don't forget your semicolons because this is C-based. All right, and now in my loop function, I'm going to do that digital, right, pin 13. We'll set it high. And then we'll do a delay of 500. And then we'll do a digital write, pin 13 low. Am I doing this backwards from how I had it on the lab? It doesn't really matter. It'll just turn it on and off. But I did low and then high. So here, let me switch these back. Low. Hi. And now let me print out our message each time. So here, print line, tick. And then down here, print line, talk. All right, so there's my program. So when you're ready to run this and test it, which means essentially upload it to the board to run it, you're going to click that little thing there, and you'll notice it brings up a little thing that says upload. This will verify, this will kind of compile the code and make sure it's okay. But if you just click upload, it'll compile it and upload it to the board. So I'll click that. I'll just use the default name for that sketch. Notice there's a little compiler thing. Oh, I did it wrong. I need to put serial.println. That's part of the serial object, not its own thing. All right, let's try again. And notice you can scroll these arrow or the error thing up here and read where the errors are, if there are any. All right, let's try again. Upload. It compiles it. And then it will tell me, okay, this sketch is using about 2K, 6% of the program storage space that's available on the thing. And that is up and working. And this board does not have an LED on pin 13. But if I do switch to the serial panel here now, or maybe that's not done. This port busy. Let me try that again. Problem uploading board. That could be because I have other things connected to this right now. Here, let me power cycle this guy. Or let me just hit the reset button. Oh wait, I think I might know what the problem is with this board. This board is different than yours. So I think I had that right. This board is completely different than yours. Yours should not have this problem. Here, hold on. I'm gonna pause this and then run it on an actual Uno board since I'm just trying to wing this and use one that's here. So let me pause this. I'll be right back with an actual Uno board and you can actually see this thing work. Hold on 1 second. Okay, I actually figured out what the problem was. It actually was not plugged into the PC with the blue wire. I had the blue wire plugged in here, but not into the PC. I was plugging in a USB cable, it wasn't that. But I don't know if you can see this now, but there's, let me see if you can see that LED blinking on the end there. It's blinking every half second. And now let's bring up the serial monitor. And notice that's actually not right there. I'm not sure why. Let me use the actual Uno. I did get one, so hold on, let me switch to that. So here's the Uno. We're going to run that same program on that one. And I think the problem with this one is the baud rate is different because it uses a different crystal on it. But here's the Uno. Notice it has a power light there. If you can see that green LED there. But it also has the LED that's going to be down here. That's going to be next to the or pin 13. So let's run this program again. Let me see if the port has changed. So tools, port. All right, COM14, and notice it's detected that as an Arduino Genuino Uno. So we're going to click that one. Now we're just going to click play. That's going to compile it. It's going to upload it to this device. I think I need to be that one. Okay, and that uploaded it, and now it's running. So let's bring up the serial monitor. And notice there it's saying, here, and if I hold the reset button, it'll stop. I'll clear the output. And let me actually change my way this output's looking. Let me put a space here. Let's do space, 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 talk, so it's easy to tell those. And if you want to upload that again, you'll click upload. You'll see those LEDs as it programs it. They'll flash as it's programming. And now you see that LED for, it's right next to the port there. Let me see if you can see that turning on and off. Half a second, half a second, half a second. And if we go back to the serial monitor, tick tock, tick tock, tick tock, tick tock, tick tock, half a second each time. So that's essentially the way you're going to do this, but you're going to write code that then changes the pin level of one of the pins. Could be 13, could be another one. You're going to connect that across to the other board. And what I would suggest doing is what I like to do when I work on these is I'll set up, even if you don't have two screens, you can put this at a size that it all fits on like the left side of your screen, kind of like over here, with its serial monitor on the left side of your screen down here for this transmitter. And then the receiver, I like to plug it on the other side of my laptop or run the wire around to the other side. So I have the left one that I'm writing code to, that's the sender. The right one is, would bring up another Arduino thing over here. You're totally able to do that. So if you get on here, I want to bring up another instance of that, you can. And then I would size that and put it over on this side and put its terminal over here. And so you can have your one machine with the program for this one, the program for the one on the other side, and then you're going to wire them together and get them to talk to each other. In this first lab, which is lab 2, the first one where they're actually communicating, is basically just going to be passing that. This one's going to be changing the channel data. In other words, you're going to put a 1 in here. It's going to set it high. And on the other side, you should see it output high, 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 high. If you put a 0 and change it low, you can see the other side say low, 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 low. So this is just establishing the channel. We're not going to do anything with it or encode any information on it right now. We just want to make sure, can you have one machine set the channel, have the other machine read the channel, and after that, the next lab, we're going to transfer some data across there. Okay, so let's go back to the, and notice this will just run forever saying TikTok. You can see that LED. Let's see if you can see that. That's matches. You should be able to see that matches the tick-tock, 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 tick-tock. Okay, so let's switch back to the presentation just for a second. And that's that sample code that I just put in. If you want, you could rewind the video and follow along and type it in yourself, or just copy and paste it from here. Note that if you copy and paste it, it might not work because the stupid word processor likes to switch out the quotation marks. You might have to retype those. It might give you an error based on unrecognized symbols or something like that. But other than that, you could copy and paste these and have them work. Let's just for fun, let's get this one. Let's do this one as well. I actually can't select these because it's in presentation mode. But, well, I'll let you do that one yourself. I think you're ready to work on the lab. So work on the lab, stay safe, wash your hands, wear a mask if you're out and about. Everybody make sure, especially if you're going to work in a group with somebody on this, make sure to be as safe as possible. If you guys live together or live in the same dorm unit and you feel like you've already been exposed to that person, that's okay. But if it's somebody else that you don't know from a different household, just wear masks when you're together. Don't touch the same things. Wash your hands. Just play it as safe as possible. And if you did get 2 Arduinos, you can totally do this on one machine on your own. All right, that's it for today. Work on the lab. If you have, as always, if you have any questions or problems or need help with anything, your Arduino hasn't shown up yet and you want to borrow one, check one out from me. That's something that I can do. I have a few of them that are my own personal ones that I could loan out if you want, but I do need to keep some in my own hands as well to be able to work on. I actually use those a lot anyway, even in business stuff, to just throw together an idea and write some code and test some things. They are great boards. Like I said, there's a whole variety of them available, range all the way from cheap, low cost, low power microprocessors up to higher power things. It's actually a good way to get started on those things. For real projects, I don't like to use them. I'll use those processors, but I like to have more control and not have it abstract things away and do things that I don't have control over. But they are good for this kind of thing. So we're going to use those for the next 4 or 5 labs, maybe 3, 4 labs. But they are something you could use throughout your career in both classes and in work hobby things. All right, that's it. I'll see you guys next time. Let me know if you have problems.